Section 1.6 is titled Graphical Transformations. In this section, what we're going to look at is how can we take graphs of functions and transform them, which means move them around, flip them over, stretch them, shrink them, etc. Before we get into all the different transformations, I want to describe them all as fitting into one or two different types. We have rigid and non-rigid transformations. A rigid transformation is one that keeps the original size and shape. Okay, examples of rigid transformations would be translations. Translations are just like sliding things around, and reflections. Reflections are flipping the graphs over. Okay. We also have non-rigid transformations. Those will change or distort the original size and shape. Now with this, you'll still be able to tell that the new graph is a form of the original, but it is going to look different. Not just sometimes in a different location, but it's just going to look different. These are your stretches and shrinkings. Okay, when we stretch and shrink the graph, we're talking about non-rigid transformations. We'll begin by looking at translations. If we have a function f of x and a positive real number c, well then here's how we define our translations here below. Horizontal translations will look like this. I'll go ahead and write them both out separately. F of x plus c, f of x minus c. If we are adding c, the graph is going to move left c units, and if we are subtracting c, graph is going to move right c units. Okay, I know that's kind of backwards what you think. You go to the left is the negative direction, yet it's plus in here, and same is true here. Go right, that's the positive direction, yet it's minus inside. Okay, for vertical you see it like this. F of x plus c, or f of x minus c. So here you see the plus or the minus c on the outside of the function. When you add, you move up c units. When you subtract, you move down c units. Okay. So just kind of sum up, horizontal translations, you see the plus minus constant c on the inside. Vertical, you see it on the outside. And horizontal, it's kind of backwards of logic or common sense. Plus goes left, minus goes right. Vertical, it follows common sense or logic. Plus goes up, minus goes down. Let's see a few examples of that. Alright, what you're looking at in my examples, I have two different ones here, and again I know the grid lines on these graphs are kind of hard to see. Just do the best you can. I think you'll get the general gist of what I'm doing, even if they are hard to see. What I've got here is an f of x. What I want to do is graph this, f of x minus 5. Okay, it's just a line segmented function. It is a function. It passes vertical line test. So let's move this funny looking function according to this up here. So we see f of x minus 5. The x minus 5 is on the inside. When I see inside, I think left and right. I think opposite direction. So the minus 5 is going to move everything to the right. 5. Just count all the points right, 5 units. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. And I can connect them once I've plotted them all out. There's my new graph. We can see it definitely looks like the original. It's the same size, the same shape. It's just in a different location. Okay, next one we see f of x plus 3. Okay, so this is on the outside. And when it's outside, we think to ourselves up and down. We go the direction of the sign, so this is going to go up 3 units. All the points, just move them up 3. 1, 2, 3. 1, 2, 3. Just keep counting them up. Once we've got them all counted up, then we can connect them. When you connect them, you just connect them left to right. That could have looked better for sure, but we kind of get the idea. It's the same shape, just moved up 3 units. Now we can combine the horizontal and vertical translations, and these two examples show that. You've got, so here's our f of x functions below. These are what we want to graph above. We've got this f of x minus 3. The minus 3 is on the inside. I'll just draw up above here. That means we're going to go to the right 3 units. Plus 4 on the outside means we're going to go up 4 units. So all of our points are going to go right 3. So this one here goes 1, 2, 3, then up 4. 1, 2, 3, 4. There's our point. Just do that with all of them. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. I can reconnect them. There's our new graph. Okay, next one, same idea. We're just gonna move the graph. The plus 3 on the inside moves it left. The minus 3 on the outside moves it down. So all the points left, 1, 2, 3, down 1, 2, 3. 1, 2, 3, 1, 2, 3. Just keep that up. 1, 2, 3, 1, 2, 3. And then 1, 2, 3, 1, 2, 3. It's almost like we're dancing and we're counting out dance steps. To there, to there, and there. So the whole graph is just sliding around, just moving around. That's translation for you. Okay, next we're going to talk about reflections. How do we flip the graphs over? We can flip them over 2 ways. We can flip them over the x-axis, we can flip them over the y-axis. To flip them over the x-axis, we would see this negative f of x. To flip them over the y-axis, we would see f of negative x. So what matters is the location of the negative. If the negative is on the outside, then our graph is flipping over the x-axis. It's flipping this way. Notice flipping over the x-axis is like flipping vertically. And just like vertical translations, the number was added on the outside, vertical reflection, the negative is applied on the outside. So that's kind of a common theme. Things on the outside affect vertical change in the graph. Likewise, things on the inside. So if the negative is on the inside, you would see the graph reflected horizontally over the y-axis. Okay, so you'd see a horizontal reflection. You see the vertical reflection a lot And I'll be honest, you don't see the horizontal one that much in practice or in examples. But this one over the x-axis, you're going to get real used to seeing that. Finally, I want to go ahead and look at the stretch and shrink rules before we jump into some examples where we might just see reflections, translations, and stretching and shrinking kind of all at the same time. To stretch and shrink a graph, we can do it one of two ways. We can stretch and shrink it vertically. We can stretch and shrink it horizontally. Okay, so we divide it up into two categories again. Vertically looks like this. I'm going to use the letter K to represent a real number and then my f of x again. For vertical, we'd see K times f of x. If K is bigger than 1, so like 2, 3, 4, 5, etc., then graph stretches, I'll say by a factor of K. If, on the other hand, K is less than 1, but I capped it at 0, so between 0 and 1, like a half, a third, 2/3, 3/4, you know, whatever, just not negative because negative is reflection, but between 0 and 1, well, then the graph shrinks. And again, by a factor of K. Okay, so just like we've seen previously, things that are on the outside of the function, K is outside the f of x. Things outside affect vertical change, and anytime we're affecting vertical change in the graph, it follows kind of like a logical, common sense approach. Bigger numbers make graph bigger. Smaller numbers make graph smaller. Makes sense. Okay. On the other hand, horizontally stretching and shrinking, everything's just kind of backwards. And the location of the constant is different too. We would see f of k times x. So we see that on the inside. Okay, so location is different. If k is bigger than 1, oops, misspelled that, then the graph shrinks by a reciprocal factor of k. Okay, and on the other hand, if k is between 0 and 1, so small, then the graph stretches, again by a reciprocal factor of k. Okay, so again, just doing what you've come to expect so far. Anytime we change the appearance of the graph horizontally, things are inside the function and they're just backwards. Bigger numbers make graph smaller, smaller numbers make graph bigger. And what I mean by reciprocal factors is, say like the k was 2, then it would shrink by half. K was 3, it would shrink by third. If k was something small, say k down here is 1/4 x, graph stretches times 4, gets bigger. Always reciprocal factors for this. Okay, let's see some example problems.